Hello learners, welcome to this course on Embedded System Design using Raspberry Pi 4 module. In this tutorial, I will be describing about how to interface a LM35 temperature sensor with Raspberry Pi 4. So the complete project and its code are available in the GitHub repository link given below. So a temperature sensor which measures temperature and it gives the output in terms of voltage or current. So here we are going to use typically a LM35 sensor which produces output in terms of voltage. So LM35 temperature sensor is a 3-pin sensor. The first pin is the supply pin for this LM35. So we can supply from 4 volt to 20 volt to this sensor. And the third pin represents the ground line, and the second pin is where we will be getting the output. So the output which we are going to get is going to be a voltage, and this voltage will be plus 10 millivolt for every degree centigrade. For example, if the room temperature is 30 degrees, then the output voltage it produces is going to be 300 millivolt. If the room temperature is 25 degrees centigrade, then in that case it will produce an output voltage of 250 millivolt. So this sensor can measure from minus 55 degrees centigrade to 150 degrees centigrade range, and it has an accuracy of about 0.5 degrees centigrade. So we will be interfacing this LM35 sensor to your Raspberry Pi 4 module. Since this LM35 sensor is an analog sensor, it gives the output voltage with respect to time. So we will get voltage variation for all the time periods. So in order to convert this analog value to a digital value, we require an analog to digital converter. So this analog to digital converter is not available in your Raspberry Pi 4 module. So we have to interface it externally. So we will be making use of a ADC0808 IC, which is a 8-bit A to D converter, which converts your analog signal to a digital signal. And after conversion process, the 8-bit data is given as an input to your Raspberry Pi 4 through this GPIO lines. Upon receiving the digital data, we try to visualize the data with the help of a LCD. So we are going to make use of a 16x2 LCD in a 4-bit mode, and we try to display the temperature in this LCD. So we are going to take a LM35 sensor, which we are going to connect it to the channel IN0. This ADC0808 has 8 channels. So 8 channels in the sense I can connect up to 8 sensors. But the conversion can happen only one at a time. At a particular time instant, only one channel can be converted. Analog value can be converted to a digital value. But this IC supports 8 channels, IN0 to IN7. So in order to select a particular channel, so here in our case we have connected the temperature sensor to IN0. So we have to select this channel. For selecting this channel, we make use of this address lines ABC. So if I provide a value of 000, then IN0 will be selected. If I give 001, then in that case IN1 will be selected. 010, IN2 will be selected. Similarly, if I want IN7 to be selected, then I have to give an address of 111. So for our application, we have used 000, so we have connected our sensor to IN0 channel of ADC0808. And to fetch this ABC as an address, we have a line called as ALE. ALE stands for address latch enable. So we have to give a high signal. So when I give a high signal, automatically this ABC values will be treated as address and IN0 channel will be selected. Then in order to start the conversion process, we have a signal called as SOC or start signal, start of conversion. So this start of conversion, again I should provide a high signal, thereby the conversion will start. Once the conversion is complete, the ADC will generate a EOC signal. EOC signal stands for end of conversion signal. So this end of conversion signal needs to be given to your Raspberry Pi 4 module, so thereby we can read the result from the ADC. So after the conversion process, the EOC signal will be generated and the result will be available in the register inside. To get the output from this register to the pins, so I need to get this output to this pins, 8 pins here. Right. So to have that, we have a signal called as OE. OE stands for output enable. This is output enable. So this output enable should be 1. Output enable should be high. So thereby the converted result in the internal register will be coming as an output through this pins. So this pins out 1 to out 8, where out 1 will have the MSB information and out 8 will have the LSB information. So this value is fed as an input to your Raspberry Pi 4 through this GPIO lines. So the MSB bit is connected to GPIO 5, then GPIO 6, 12, 13, 16, 19, 20 and the LSB bit is connected to 26. So after reading the value, we are going to display it on a LCD. So LCD, it can operate in 8-bit mode and a 4-bit mode. Here we are going to use 4-bit mode because we will be using less number of GPIO lines. So we take D4, D5, D6, D7. It is connected to your 22, 23, 24 and 25. So if I want to send the 8-bit data, for example 0x33 I want to send, what we will do? First we will send the upper nibble. We will send the upper nibble and then we will send the lower nibble. Nibble stands for 4 bits. So first I will send the upper nibble and then we will send the lower nibble. We also have some control lines like register select. So this RS stands for register select, which indicates whether we are sending a command or a data. So if this RS is 0, then the value which is given through this D4 to D7 will be treated as command. If RS is 1, then the value which we are giving through D4 to D7 will be treated as data to be displayed. So what are commands? Commands are nothing but I want to clear the buffer inside. If I want to make the character to move towards left or right, or I want to initialize the 16x2 LCD, so such aspects will be treated as a command. Data, whatever character which I need to print here, for example temperature 30 degree, so this 3 is a data. So in order to get a value of 3, I have to provide a ASCII value of 3. ASCII value of 3 should be sent to the LCD. So this will be treated as data. So in order to select whether it is a command or data, we make use of this register select line. Then in order to provide a valid data is available in this D4 to D7, we make use of a enable line. So enable line will be a high to low pulse. It will be a high to low pulse. Then the signals, valid signals at D4 to D7 will be latched and it will go to either command register or data register depending upon the RS value. If it is 0, the D4 to D7 will be latched and it will go to command register. If RS is 1, D4 to D7 will be latched and it will go to your data register. So this is how we try to connect the LM35 sensor with Raspberry Pi 4 module. So whenever I have an ADC, the important factor is the resolution of the ADC. How to calculate the resolution of an ADC? This is a formula to calculate the resolution of your ADC, which is V reference divided by 2 power n minus 1. V reference stands for the reference voltage. So depending upon our reference voltage, the input voltage will swing. For example, if I give a reference voltage of 5 volt, in that case my input can swing between 0 to 5 volt. If my reference voltage is 1.5 volt, then the input voltage can swing from 0 to 1.5 volt. So depending upon my reference voltage, the input voltage swing is decided. Same way, N stands for whether it is a 8-bit ADC or 12-bit ADC or 10-bit ADC, the N value determines the output bits, how many bits we are going to get. So since we are using a 8-bit ADC here, we have a value of 2 power 8. So in order to compute the resolution, we take the reference voltage 5000 millivolt, which is equivalent to 5 volt, divided by 2 power 8 minus 1, it comes about to be 19.61 millivolt. So this is the smallest voltage change which can be represented in a proper binary bit pattern. So that we call it as a resolution. Smallest voltage change which can be represented as a proper binary bit pattern. For example, if the converted value, after conversion I am getting a value like this, 8-bit value. So the decimal equivalent will be 15. So what is the voltage given to the ADC? We have to multiply this 15 with the resolution of your ADC, 19.61 millivolt. So it comes about to be 294.15 millivolt. So this is the input voltage given to your ADC. So from this, if I want to calculate the temperature, we already know that 10 millivolt variation for every 1 degree centigrade. So if I want to convert this voltage into temperature, we divide this voltage by 10. So thereby I get 29.4 degree centigrade as an output. So this value I can display it onto the LCD. So here we are going to use Proteus 8.13 professional software, and the language of programming is going to be Python. So here I show a typical circuit diagram which we built using Proteus 8.13. So we take a Raspberry Pi 4 module, and this Raspberry Pi 4 module is connected with your ADC 0808 IC and a LCD. So first let us take the ADC 0808 IC, where I took LM35 temperature sensor and it is connected to IN0. To select this channel, we make this ABC to be 0, 0, 0 by connecting it with ground line. To indicate this as an address, we provide the ALE signal through your GPIO line 02, GPIO 2. Then we provide a reference voltage. So here I am going to give VDD 5 volt as a reference voltage. So our input voltage can swing from 0 to 5 volt. Then this ADC requires a clock signal. So it takes approximately 10 clock pulses to produce our converted result. So we can provide a clock signal of about 500 kilohertz to this ADC module. Then we have a start signal, so which indicates start the conversion process. So this signal will come from your Raspberry Pi 4 module through this GPIO 21 pin. Once the conversion is complete, this ADC IC will generate a EOC signal. So this EOC signal will be communicated to your Raspberry Pi 4 through this GPIO 7. In order to get the result, converted result will be available in the internal register. In order to get this result out through this out 1 to out 8 lines, we make use of this output enable line. So this output enable signal, again it will be coming from your Raspberry Pi 4 module GPIO 3 pin. So once we assert this output enable line, the result will be available through this out 1 to out 8, where out 1 will have the MSB data and out 8 will have the LSB data. So this signal MSB to LSB signal will be connected to your Raspberry Pi through this GPIO lines 5, 6, 12, 13, 16, 19, 20 and 26. So we read this value through this GPIO lines and we send it to the LCD. So LCD is connected in a 4-bit mode. As I said, it is connected in a 4-bit mode. So we take D4, D5, D6, D7. So these 4 lines are connected to your 22, 23, 24 and 25 GPIO lines of Raspberry Pi 4. Then we have two control lines. RS register select is connected to 18 and enable line is connected to 27. So one more control line RW bar, we have connected it to ground, meaning we are going to do a write operation. Then we give supply to LCD and VSS to ground. VEE is for contrast adjustment. So contrast in the sense we can vary the pixel value, pixel brightness. So that we can connect either to a potentiometer. So here I have connected it to a ground, which means I am going to have a high contrast. And in simulation we will not be able to see any variation. In hardware you can able to see a variation. So anyway I am going to connect this VE to a ground. So this is how a temperature sensor is connected to your Raspberry Pi and it will be displayed onto your LCD module. Now let us look at the programming part. So in order to make use of the GPIO lines, we import the package rpi.gpio. Then in order to use the delay function, we make use of a time package. Then we try to initialize the variable pin GPIO pins. GPIO 2 is ALE, 21 is start signal, 7 is end of conversion, 3 is output enable, and the input lines to the Raspberry Pi ADC converted result to the Raspberry Pi is given to this 8 pins 26, 20, 19, 16, 13, 12, 6, 5, where this 26 GPIO pin represents the LSB bit and 5 represents the MSB bit. Then we try to initialize the LCD pins. RS is connected to 18, enable is connected to 27, D4, D5, D6, D7 is connected to 22, 23, 24 and 25. So next step is we have to initialize the data direction and what type of pins we are going to use. So Raspberry Pi supports board pin configuration or IC pin configuration. So here we need to set that I am going to use a IC pin configuration. BCM stands for Broadcom IC. So we will be using a IC BCM2711, which is available in your Raspberry Pi 4 module, ARM Cortex processor. So I am going to define that we are going to use the IC pin configuration. Then we need to set the data direction. So ADC data pins are set as input. ALE start and output enable signals are declared as output lines. End of conversion is declared as input line. And for LCD, RS enable D4 to D7 is configured as output lines. So here we set the data direction of the pins. Then we write a function for enable line. So enable signal should go from high to low signal. So for that we define a function here, pulse. So we can give the enable signal here through this pin and we make that pin to be high for 1 millisecond and then it will go to low. So high to low pulse is generated. Then we define a function for reading the ADC value. So to read the ADC value, first we need to enable the address. For enabling the address, we have to set the ALE signal. So ALE signal is set as high to low pulse. So here it is set as true and here it is set as false. So we will be generating a high to low pulse. Then to indicate the start the conversion process, again the start signal is set with a high to low pulse. High to low pulse. So here it is set with high. After 1 millisecond it will go to low. So we are generating a high to low pulse for both your ALE and start signal. So once the start signal is given, the ADC will start converting the input data. So upon completion of the conversion process, it will generate an EOC signal. So we are going to read that EOC signal here using this command. If this EOC signal is 1, which means we have the converted result. In that case, we set the output enable to be true. So thereby the converted result in the internal register will come out through the pins out 1 to out 8. So first I am setting the value to be 0. So this is the variable in which we are going to get that 8-bit converted result. So we are going to take one by one. So value is set with 0, which means it is 0, 0, 0, 0, 0 0 0 0. So this is LSB bit and MSB bit. So all the bits are set with 0 initially. So now using this for loop, I am going to read one by one. First I am going to take this LSB bit, read it and put it in this location. Next this bit I will read and I will put it into this location. Next subsequent bit. Like that I am going to do it for 8 times. So my I changes from 0 to 7. When I value is 0, I am going to read for this position. When I value is 1, I am going to read for the next position. When I value is 7, I am going to read for this MSB bit position. So we read the inputs here. We read the corresponding pins. Then set value to be 1 in that position. If my input reads 0, then this if statement will not execute, so that value will be already be set as 0. If the particular pin as 1, in that case we are going to set that particular location to be 1. So let us see this with an example. So let us assume after converted result I get something like this 0 1 0 1 1 0 1 1. Okay, some input data. I have given some input and ADC after conversion process, this is the output it generates. So now I am going to read this one, right? So first my I value is 0. When my I value is 0, so here I am going to read ADC underscore data underscore pins of 0. Pin of 0 is nothing but 26th pin. GPIO pin is 26. So I am going to read the value from this 26. When I read the value from 26, I get 1. Right? I get 1. So 1, this condition gets satisfied. So what we do here, we take value or with 1 left shift by I value is 0. So 1 is left shift with 0, which means we are not going to do any shift. So what we do, we take value. Value is nothing but already it is set with 8 zeros. Now we are going to OR with 1. So 1 means 1 OR function. When I do it, what happens? I get 1 here, other bits will be 0. Now you can see that I have got the information regarding the 0th bit. When I changes to 1, when I changes to 1, what happens here? Now this I is changed from 0 to 1. Again I am going to read this data, ADC pins. So this next bit is also input is 1. In that case what I am going to do? Again I am going to take 1, I am going to do a left shift by 1 time. Right? So left shift by 1 time, now the 1 will appear here. Right? Again I am going to do the OR operation. So now what happens? I get 1 1 0 0 and 4 zeros here. So now the next bit information has been gathered. So like this I am going to do it for all the bits from I equal to 1 to I equal to 7. So all the 8 bits I am going to do, then I will get this result, 8-bit value in variable value. Then I make the output enable signal to be false, then return that value which we have captured. Then we are going to write a function for sending the nibble. Nibble stands for 4 bits. So this is for your LCD. So LCD we have to send the data nibble by nibble. So first we will be sending the upper nibble, then we have to send the lower nibble. To do that, what we do is we take the nibble. For example, I want to send data 0x33. Let us assume I am going to take 0x33. So first I am going to send this upper nibble, right? So 3, which means 0 0 1 1, right? So I take this nibble and it with 1. Okay, so 0x001, right? So we are going to do AND operation. So what we get here? 0001. So this bit I am getting. So this bit I am sending it through D4. Next, in order to send the next bit, so this is the next bit, I have to send this next bit. So what we are going to do? We are going to take the nibble, right shift it by one time. So what happens? So initially it is 0011. So I am going to do right shift by 1, which means it will be 0001. Now this value again I am going to AND it with 1. So AND it with 1 in the sense 0001. So I get 1 here. So this one I am going to send it to D5. Again next, what we are going to do? We are going to take 0011. So this is our nibble. Now I am going to do right shift by 2 times. 2 times we are going to do. So what happens? 0, 0, 0. So 2 times it will be 0. So after doing right shift by 2 times, then I am going to AND it with 1 again. 1, 0, 0, 0. So when I do that, I get 0 here. So this 0 I am going to send it to D6. Same way the D7 bit also will be enabled. So we provide the signals from D4 to D7. Then in order to latch this information, we generate a enable signal high to low pulse. So this is a function for sending the nibble values. Then we are going to write a function for sending the byte. So as I said, 0x33. First what we have to do? We have to send the upper nibble. And then I have to send the lower nibble. So we have to take the value and I am going to set the mode. So mode 0 means it will be treated as command. 1 means it will be treated as data to be displayed. So we set the value RS is either 0 or 1 depending upon whether I am sending a command or I am sending a data. Then what I take this value, which is a 8-bit value, right shift it by 4 times. For example, if I take 0x34, I am going to do right shift by 4 times. So what happens? I will get output as 0x03. This 3 will come here. Right? So this is the output. So this output I am going to send it here and I am going to send it out. So after sending the upper nibble, so we have sent the upper nibble first. Then we have to send the lower nibble. Lower nibble is 4. Right? So for lower nibble, we take the value and it with F. So we get the lower nibble and send it here. So for that we make use of this function LCD underscore send underscore byte. Then we write a function for initialization of your LCD. So we give a value 0x33 stating that our LCD will be in a 8-bit mode. And this value is nothing but a command. So it is specified as 0. Mode is specified as 0. Next, I want to convert this 8-bit mode into 4-bit mode. So we have to transit it. So for that we give a command called as 0x32. Then to set it as a 4-bit data mode, we will be setting it as 0x28. Then other functions like display on, cursor off, we have to give a command 0x0c. For entry mode, 0x06. And to clear the display in the register, we give 0x01. Then we wait for some 10 milliseconds. So this is the initialization part. Then we write a function for sending the message using this LCD underscore write, where we get the message. So message is something like temp equal to 31 degree centigrade. So we have to take each character T. I have to convert it into ASCII value and send it to LCD. Then E, convert it into ASCII and send it to LCD. So like that we have to take character by character and we have to convert it into ASCII and send it as ASCII to your LCD. So we are going to take this message, we are going to take one by one the character and convert it into ASCII here, and I am going to specify, I am going to send a data to be printed. So mode is 1, which indicates this is the data to be printed. So using this function, we can send the character to your LCD. Then I have to say that whether I am going to print the data in the first line of the LCD or second line of the LCD. So here we are going to use a 16 cross 2 LCD, which means 2 rows are there. In each row I can display 16 characters. So to indicate that, we are going to set the cursor value here. So if the address is 0x80, when it will be set as 0x80? If I select line 1. If line 2 is selected, the address will be set as 0xC0. So we send the address and we say this is a command. Then we define a main function here. So in main function, first step is we have to initialize the LCD. After initializing the LCD, we are going to run the program infinite number of times. So we set the while condition to be true. So we read the ADC value and put it into this variable digital. So this value should be converted into voltage. So what we do, we take that ADC value and multiply it with the resolution. Okay, resolution is nothing but 5 volt divided by 2 power 8 minus 1. So this is nothing but 5000 millivolt divided by 2 power 8 is 256. 256 minus 1, which will be equal to 255. So 5000 is here, 255 is here. So we get the voltage value. Once I get the voltage value, I can convert it into a temperature. How to do it? Divide it by 10. Because for every 10 millivolt variation will be obtained for 1 degree centigrade. So we get the temperature here. So I am going to set the cursor to be in first line. So LCD has 2 lines. I am setting the value to be in first line, and I am going to write the data, which is temp. And we are going to say that I am going to use 1 digit after my decimal point. And we try to put the temperature there. So for 1 second it will be retained. Then again the ADC value will be read, converted into voltage, converted into temperature, and display it onto the LCD. So this main program, we are going to call it using this function. Thereby we read the temperature value from ADC 0808 IC and display it onto the LCD. Now let us look at the simulation part. So here we have a typical circuit. So temperature sensor is connected to IN0, ABC is connected to ground, and ALE is connected to GPIO02, and the reference voltage is given as 5 volt supply, and a clock signal of 500 kilohertz is connected to clock signal. Start, EOC, and output lines and output enable line are connected through this GPIO lines. Then LCD is connected in your 4-bit mode. Source code, the complete program which I explained just now, is available here. You can see the importing the packages, setting the pin values, GPIO pin values, set the data direction for the GPIO pins. Then we write a function for enable line, high to low signal. Then write a function for reading the ADC signal. Then write a function for sending the nibble, writing a function for sending a byte. Then initialization for writing a message onto the LCD. Set the cursor line of your LCD, then a main program. So main program is where we initialize the LCD, read the ADC values, convert it into voltage and then to a temperature, then display it onto the LCD. So we call this main program using this code below. So upon writing the code, compile this code, then go to the schematic and execute it. See, the temperature is set with 35 degrees and the LCD shows 35 degrees. So if I increase or decrease the value, for example, I am keeping it as 30 degrees. You can see right now it is set as 29 approximately. It is trying to show the temperature values. If I increase it, 40 degrees. You can see for every 1 second it will try to read the ADC value and it will try to display it. So this is how a temperature sensor data can be acquired in a Raspberry Pi 4 module and the value can be displayed onto your LCD. So in this tutorial I discussed about how to interface a LM35 sensor with Raspberry Pi 4. So important thing is Raspberry Pi 4, it does not have an inbuilt ADC. So we have to use an external ADC 0808 IC which gives the 8-bit converted result. That converted result goes as an input to your Raspberry Pi 4 module and then that value is displayed onto your LCD. So thanks for watching. Please like and subscribe for more technical learning. The complete code and simulation of the project is available in the GitHub repository link given below. Thank you.